So today we're going to be talking about the traveling salesman problem, salespeople problem, and how we can use ArcGIS Online Proximity tools to solve it. So what is a traveling salesperson problem? Abbreviated TSP. So essentially, this question asks us, we have a traveling salesman going from one city to another, kind of going through maybe a series of different cities to do their door-to-door sales for a day. And we want to know what the shortest route possible is between each city and including their drive home, usually. And so when we think about this question, obviously we think very narrowly about the kind of sales perspective, but there are a couple different ways to kind of rearrange this question and think about different ways it could be applicable. So for example, I think the most common thing you would think about is going to be our general navigation. You're using your iPhone or your Apple Maps, Google Maps, right, to get from point A to point B, mapping with live traffic. Those are sort of like traveling salesperson problems, right? We can also talk about minimizing the cost for that travel. So I think probably the most modern way we think about this question is going to be like for package delivery. So say you're going to be like a USPS, right? And you want to make sure that you can deliver your packages to all the homes in a certain amount of time. That's, this question, how can we do this as efficiently and as quickly as possible? The last one there, I like to think of this as almost like a reverse traveling salesperson problem, right? So instead of thinking about things in terms of I have to hit all of these different points, what about those points enables us to reach it within a certain amount of time? So for example, we can think of maybe back in that kind of package situation, maybe you have a facility where all of your packages are being shipped to, and then they're being delivered throughout the day. What would be the range of that facility? Could we add more facilities to make it a little bit faster or more efficient to deliver those packages? And all these questions can kind of be answered with this Esri suite of tools that we use to look at like different networks. So specifically like roadway networks. All right, so we're gonna get into kind of the fun, nerdy stuff here. I had a field day with this, but we have this question in computer science of P versus NP. And these are some big concepts that we're gonna try to narrow down and just break down a little bit. I decided it'd be fun to kind of touch on, but we have something called polynomial time and non-deterministic polynomial time. The idea is essentially just to make it as simple as possible. Some things can be solved relatively quickly and some things cannot. And so unfortunately, our traveling salesperson problem falls into that second category where we can kind of verify if something is very quick or is the best possible route pretty quickly, but trying to actually find it or solve it can take a lot more time. And so in that second or that third bullet point there, we can think about, imagine you had a list of every single possible route that you could be taking. It's really easy to look at that, and for a computer especially, and say the shortest one among this whole list is this one. But to try to kind of calculate that in real time and figure out, exactly what that is, that takes a lot more time to process. And so that's where we think about this NP. It's a larger problem, more difficult problem for us to solve. Some other examples of this, Battleship. So if you guys are like a really big fan of games, so Battleship and Sudoku are examples of kind of this NP problem. It's really easy to verify a board of Battleship or a Sudoku board to make sure it's valid, that these things make sense, that they're good to go, right? We know that it's abiding by the rules, so to speak, of the game. I can tell if someone's cheating in Battleship really quickly. They're not placing all of their ships, or their ship is placed in a spot it can't be placed in, right? But for me to then play a game with them and try to figure out which ship is, what their board looks like, what's the how can I beat them, that takes a lot more time to kind of solve and calculate. And so your computers in the background, when they're thinking about things like the traveling salesperson, are doing the same kind of logic in the background, and it just takes a lot more time. So the solution to that, and all three of these kind of classify as these NP problems. So we've got our Battleship, Sudoku, and traveling salesperson. To make this really simple on ourselves, we use algorithms. Okay, so we have Esri now, kind of going back into the world of GIS a little bit and away from that computer science stuff. In the Esri world, we usually use the network analyst suite to determine things like this, to figure out the fastest way possible. And unfortunately, my little GIF it's not actually going through, but we'll talk about this. We have a specific algorithm that we use to determine what the shortest viable path is. And so it kind of froze at a pretty decent spot here, which I guess is great. But the way it's supposed to work is starting down here at the little A. We are going to be looking at the other paths and seeing what's the shortest one possible. So in this case, we see 14, we see 9, and we see 7. Not sure, my mouse won't show that, unfortunately. And we're going to go with 7, which brings us down to that number 2 down there. That's the shortest possible route for that instance. As it kind of considers and moves up, so it sees the 7, or sees the 10, the 7, the 15. Obviously, 7 means going backwards. We want to go forward, so we're going to go up the 10 to the 3. And then we're going to go up past that one to either 2, 9, or 11, or 10, I guess, too, if you want to go backwards. But again, it's always thinking about moving forward and picking the shortest one possible. So it goes 2. The last one at the number 6 node there, we're trying to get to that B ultimately. The fastest way for it to go from here is going to be to check that 9, not the 14, or the 2, because both of those go backwards. There's only one left. And you can see how it was able to figure out ultimately a path that is relatively quick, right? But technically, that's not the shortest path. If we were to add all these distances up, the 7, the 10, the 2, and the 9, I believe we get, what, 28? But then if we were to go from the 1, the 6 to the 5, that kind of outer edge, the 14 to 9, that's going to be a shorter path technically than the path it ended up taking. It's just that the algorithm can only solve things one at a time, so it's trying to suss it out as it goes, as opposed to, again, being able to just solve it immediately. That's a lot more computationally difficult for computers. But these algorithms are pretty good, and in the case of this Esri one, we're actually able to add a couple things. So one-way restrictions, for example, on roads. You can think about maybe yeah, that route would have been faster overall, but it's a one way. We can't drive that. So the algorithm can kind of accommodate that and prevent us from traveling ways that we wouldn't be allowed to. All right, so now coming into more of these analysis tools, specifically in the Esri world. So in Map Viewer, the new Map Viewer, Map Viewer Beta, however, whatever version of Enterprise you're running, or ArcGIS Online, right? The official current Map Viewer that we're trying to use more frequently here. In this world, if we were to go on the right-hand side, you have that little, it's a square with the 3 circles above it, and that lets us use our analysis tools. And then if we want to specifically go into little tools, it's that little hammer icon. And you'll see we have this list of all these different options here. And today we're going to focus on that use proximity, because that kind of helps us best address the salesperson problem. So proximity tools, I'm gonna go over 2 major ones for today's kind of demo. So there's several different ones that are available, but for the planning routes, that's gonna be your very typical, we're just going from point A to point B. Usually you can have multiple point Bs, right? So you're going to multiple stops per day. And what's kind of nice about this too is using Esri's algorithm, we can also implement a couple of different restrictions. And we'll see what that looks like when we go ahead and demo this. But it's a really cool way to kind of do not only an individual traveling salesperson, but multiple traveling salespeople. Maybe maybe you have 2 different facilities and you have people leaving at different times. So you can kind of solve these different elements with this tool. The output that we're going to see here, and probably the most useful way that we can visualize this, we're going to have lines that represent the full vehicle routes from their starting to ending positions. So it should be fairly straightforward to follow. And again, once we run this, we'll be able to kind of see more of what this looks like. The cost, I do want to say that there is a credit cost associated with using these tools in ArcGIS Online. And so we just want to make sure we're aware of what those are. In this case, it's going to be 1 credit per vehicle route. So say you have multiple routes you're calculating, you have multiple individuals who are going to be starting on that path, and they're each going to consume a credit. The second one here is our generate travel areas, formerly known as create drive time areas in Map Viewer Classic. So what this is, it's kind of that other bullet point we mentioned a little bit earlier about the sort of like reverse traveling salesperson problem. So now we're going to be taking our stops and saying, okay, how far can we reach from this stop? So we can think about like that example again with the shipments, right? If we have different shipping facilities, what's the total reach that we have from that location, in a certain amount of time? How far can our trucks get away from this place and make their deliveries within a certain time frame? Is kind of what we're asking with this type of question. Basically, we're going to throw in our points, any restrictions as well on here. So that same concept before, where we're sort of using an improvised version of that algorithm, where we can introduce these restrictions to kind of better emulate the real world and show potential problems that might come up. It's going to solve for that travel time. And then these polygons that come out are going to represent that full coverage area for a vehicle in a typical drive time. And these cost half a credit per service area. This here, so basically we're just going to see it in action. And so I kind of want to give us a little bit of a prompt. So we have a place where we can start with the demo. And I thought of it, I think when we think about the traveling salesperson, it's usually a sales minded, but there are different ways that we can kind of conceptualize what these tools are doing or how they can be applied. And so for me, we're in Southern California here. So we have, a lot of wildfires going on. And so it just seemed really pertinent to kind of talk about some of the ways that we can use GIS to better assist some of these strategies that firefighters and different emergency responders employ in order to combat wildfires. So in this case, we're going to look at how we can make sure that firefighters receive their supplies, and then we're going to look at where we might place future fire stations. So using that other element that generate travel areas, right? We're going to see, based on how far these fire stations can travel, where might be a good spot to place a new fire station to maybe better assist with the wildfires or just fires in general in the future. These will hopefully make a little bit more sense as we kind of jump into the data, which I'm going to go ahead and we do have a bit of data here that I went ahead and put together. So we are looking currently at the Escondido, San Marcos area, kind of in the North County area of San Diego. And so these are not, a real location where there's currently active fires, at least as far as I'm aware. And these also are not true fire station locations or shelter locations. I just found some vacant lots and thought they made sense to kind of demonstrate this. So I just totally threw it out here, totally just to model and kind of get an idea of what these tools can be used for. These aren't meant to emulate the real world or anything like that. So what I'm going to take us through is we essentially just have these couple different points. So we have our fire stations kind of all congregated around this center city. This here is Escondido. And as we move up into the northeastern part, we do have a shelter that I put together. And then out here to the west, kind of near the San Marcos area, we have another shelter. And so the idea is we're going to start at one of these shelters, so both of them, and we're going to travel into the city and see what it might look like to deliver supplies to each of these. Way we accomplish this is on the right-hand side. We do have this little analysis widget here, and if I click on it, it's going to open up an analysis little window, and we want to look at our tools. And again, a lot of different options in here, stuff that we can play around with, but for us, we are going to focus on our use proximity and specifically this plan routes down here. So when this opens up, we have a couple different parameters that we can place in. First and foremost, we're going to use our GIS layers. So we're going to put our start layer, which for us is going to be our shelters, because again, we're starting at our shelters and we're going to our fire stations as the individual stops. So shelters in here, we'll put our stops in here, our fire stations. And then you want to put in a route ID field. In this case, it's basically just a name. This is just so that later down the road, you can identify which route is going to be from that shelter 1 and what's from the shelter 2. So it's good to have something to identify these later. We have the option to put in barriers, which we will demonstrate in a second here, but let's maybe take it through just kind of like a very simple one first, and then we'll go back and add that in and show what that looks like. The travel mode, we're going to use drive time. There's a lot of different options here, but we're going to stick with driving time. It's the most relevant, I think, to us in our scenario here. And we do have a departure time. I think it just pulls in the current time whenever you load this in. It does use real-time traffic, so keep that in mind. So if you're trying to find a very specific, maybe like a rush hour type analysis, make sure that you're setting this to a time that makes sense, or a date even of when you're actually going to be either doing this, say you're making deliveries, or when you're planning for it. So I would for sure try to keep this as close as possible so you get that real world traffic scenario. Max number of vehicles to route. So we only have 2 possible because we have our 2 shelters. Whoops. And so let's say we had a third one, you could do 3. That's all this is really saying here. The max number of stops per vehicle. So in this case, we're envisioning we have volunteers, right? We don't want them to be overworked and we're just trying to utilize their time as efficiently as possible. And we have enough to go around. So maybe we'll say we want to have 3 stops per vehicle, right? We have 5 different locations. So at most one can do 3, the other will do 2. So we can kind of limit it that way. So we're not over encumbering our volunteers. For the time spent at each stop, this is just to say, you're probably not going to just drive by the curb and throw things out the window. You're probably going to stop, get out, hand them something, get back in the car, get driving again. So it takes a little bit of time to do that. I'm going to say 10 minutes for this. Why not? Absolutely, you could leave this at 0 if you really just want to know how to hit all those stops. But I think that it helps to kind of emulate the real world. And in the real world, we're going to be stopping and doing things. We're not just going to be moving constantly. You can also limit the max time per vehicle. I'm going to leave this on and actually lower it to 60 just to show what this looks like. So essentially what you can do is you can say, hey, for this particular day, we're only going to be working for this number of hours. In this case, 60 minutes, just an hour. So we can kind of limit and see where maybe some of our deficiencies are. Where can't I reach within a certain amount of time? It helps for planning if you're maybe working over 2 days, right? 2 or 3 days, right? So that way you have an option to say, okay, I'm not gonna be able to hit all of these, but how can I split up that workload between those days to make sure I hit all of them? So I like to kind of start this a little bit low and maybe build up so you can see as much as you need possible. In this case, we'll just keep it at 60. We do want to give this an output name. I think I called this something like supply route 1. You can maybe name it something a little bit more efficient. I do want to say though for this, I did have a problem where I tried to name it with a number in the front that does cause problems for the tool. So I would put in any numbers, dates, things like that at the end of the name. I wouldn't lead with them because that has caused problems for me in the past. Yeah, the options include a route layer. These are kind of cool. So basically, they're going to work like a such like a Google Maps or Apple Maps to give you turn-by-turn directions. So we won't go into too much detail on those and how they work exactly, but just know that you can click this and it does generate additional outputs over here. And if you hop into these, it'll basically just let you see the turn-by-turn directions, which is really useful as well. All right. Last thing we want to do is go ahead and estimate our credits. And when we do that, we see that we have 2, which makes sense, right? We're generating 2 different routes for shelter 1 and shelter 2. And we saw earlier in the slides that if we go from, we have the option to go from, for each route, basically, is what the credit is being cost. So it's 1 per route. And so we're creating 2 routes. So that's why we're having 2 credits here. I'm not going to run this right now, only because when I did, it takes a long time. I actually went ahead and got this ready for us. So if I were to turn on this first delivery here and maybe close a couple of these things just so that we have a little bit more room, you can see that we were able to create our little routes. And so it'll always start, number 1 is going to always be the starting position. So in this case, we start at the shelter, and then it'll count up 2, 3, 4, however many stops it was able to get to. So you'll notice we said 1, we went along this road here, went up the freeway, came down, went over to our number 2, continued back onto the freeway again, and back around, ended at number 1. So we indicated that we wanted to return back to our starting position again. So this, if you'll notice, we did actually, and same thing for this number 2 shelter, same idea. We have a little route that we can follow and it shows all the places we hit, but we do have these little outliers. This fire station 4 and 5 were not hit by either of these. And that's because we had that time restriction. So this means that it took us an hour to go all the way here and back, and we didn't have enough time to get here to 4 and also include the time to go all the way back again. So because of that, we know that we're going to have to figure out some way to accommodate these. So the way that I solved this is essentially I went back over to our analysis. I removed this time limit max, and you can also just increase it too if you're more comfortable doing it that way. And I ran this again and got something that looks like this. So you can see how this is kind of like an incremental type of game that we're playing, right? There's a little bit of kind of finagling and trying to get things to work the right way. You have obviously these different parameters, these restrictions that you want to play with. And so we're just trying to figure out the best possible way to ensure that our supplies can make it to each of these fire stations. And so sometimes that means you have a time restriction. Maybe you want to increase that. Maybe you want to remove it altogether. This just lets us kind of see where can we not reach. And so how can we make adjustments to make sure that we do reach once we actually run through this. So I did talk about this, but over here in our analysis, we also have the option to introduce barriers. And so the way that we want to approach this barrier here is we want to add a polygon, line, or point layer to this little barrier, and it'll calculate with that. So what I did was I created a travel barrier for us. And I really like to use polygons. So I'm going to go ahead and pop this in here, our travel barriers, so it can run with it. If you zoom in here, it can be a little bit tougher, I think, to use points and lines because you kind of have to be pretty accurate with where you're going to be placing like the cutoffs, right? So essentially what we're doing with this barrier is we're saying we can't drive on this road, right? For whatever reason, we are not able to go on here. In this scenario, maybe it's like a road closure. This freeway is closed from this extent to this extent to minimize traffic flow as people evacuate, something like that, right? There might be another reason why we want to restrict these roads during times of emergencies. And so to emulate it, I've created this polygon. And to be honest, we could have made this a little bit more accurate, probably. It does it's essentially going to exclude anything that falls within this polygon boundary. And so we may have wanted to get a little bit closer to the freeway so that some of these side roads along the freeway aren't also excluded. But either way, I do think the polygons tend to be the easiest to work with. The points and lines can be a little bit tough because you kind of have to be very precise about where Esri's network, the road network is, to block them off. So I like to just use polygons. I feel like it just makes sure that those things are excluded. So essentially we'd go through here, we would just go ahead and run this again, but just having this little polygon barrier introduced. And by doing so, let's go ahead and hop back out again. And we'll go ahead and close this just to make sure we have a little bit more room. Our new delivery line looks something like this. And so you can see here how we've excluded this freeway. So initially it had us drive all the way up here and then come back down. Now it's telling us, okay, we're only going to take these side roads to go all the way through. You can actually see how intricate and precise this gets, right? Where, because we're going out and back again. And so one of these, for coming back, it must be faster to go a different way. Or there could be one ways, right? So that's why you have these little islands that get formed here. That's just a little bit more efficient to go a different way when coming back. And we can see that we've now effectively excluded this entire segment of the freeway. So it does give us that option when we're coming through here. Okay, so pivoting away from these little supplies, we're going to take a look at our resources again, and we're going to focus on our fire stations. So when we're doing an analysis to figure out like the range of these fire stations, how far can we go with these? We are usually speaking in terms of like a buffer of some kind. And we can go ahead and generate those fairly efficiently here. Again, in our analysis tool, if we click a little back arrow or this little back button down here, we have the option to create buffers. And when we do so, we're just going to input our fire stations. A lot of items in here now. We're going to do our distance values. So we can't do something like a drive time like I talked about. So I had to calculate it after the fact, or before the fact rather. I'm going to say 2.67. That is just saying we're going to be traveling 40 miles per hour, and we're going to be traveling for 4 minutes, which should be approximately 2.67 miles that gets out of that, right? So that's the reason why I come up with this. In the second scenario we'll show, it actually can just do the 4 minutes itself, but you may have to calculate if you're going to be doing this sort of buffer calculation. So you have the option to do our miles. You can do different units if you wanted to. I like the overlap so I can see all of them separately as opposed to dissolving them into one giant blob. I kind of want to see individually for each station how far they can reach. If I were to go ahead and run this, it's not going to let me. I'm going to just put a name really quick here. Oops. If I go ahead and put our estimate credits here, you'll see it's actually very cheap to do this. So if you want to run buffers, it's not really a huge deal. And we do run this. Again, I didn't want to spend too much time generating them in real time. You'll see we have these massive circles. So by looking at this, if we're looking at this and saying, hey, how far can a fire station get in 4 minutes, assuming they're driving at 40 miles per hour, right? 2.67 miles. This seems to indicate that we have a huge coverage. Pretty much all of Escondido, this urban area, is covered. We're pretty much set, right? Like everything looks more or less good. These circles don't really represent, though, how far a fire truck can travel within 4 minutes. And we can think this because obviously a fire truck isn't going to drive in a straight line up into mountains and things like that, right? They have to abide by the roads. And so the kind of big picture with all of this stuff is we're all using this sort of underlying road network to determine how fast or how far can we get to a certain place. These buffers just don't really do it for us. Maybe for a fire, like a fire helicopter, right, to do some drops, like for fire retardant or for water drops, right? Maybe this could be useful because obviously a helicopter has a lot more range of where they can fly to. They're not limited by the roads, but for a pure situation where we're just trying to drive along the road, it's a little bit difficult to tell from just this how far we can travel, how much coverage we actually have. So we're going to run that second tool that we mentioned in our slides earlier, this generate travel areas. So for this, it's a very similar setup. We're just going to place in our fire stations as our starting point. We're going to be in the drive time mode. Again, there are other options, but this drive time is probably the best one for us at this time. We can add these cutoffs in, and you can even do multiples of these if you want to do more, but we'll just stick with our 4. So we have our 4-minute drive time, right? So we're using our minutes as our cutoff. You could go further into seconds and hours if you wanted to. Our travel direction is we're going away. If you think about it, we're starting at a fire station. It's how far from that station can we go? So that's why we're using the away option. Um, I'm not going to specify a time here only because we're thinking in terms of fire station response, emergencies. I don't know if it's going to be during traffic hour. I don't know if it's going to be when things are calm. It can happen anytime, right? So we're going to keep this as time unspecified. You could do a traffic hour time to kind of get that really conservative. How much could we do when there's people on the road? But I'll leave it unspecified just so we can kind of do average times, just to kind of get a big picture idea. We're going to use the overlap policy again, and I love to generate the detailed polygons. I just think it's the most useful and they look the nicest, so it's easier to tell kind of exactly how far they can reach. And then we'll give this a name. We will call these drive times. Or oops, I guess we'd call them travel areas, right? That's what we're trying to generate here. If I were to estimate our credits, we can see that we get 2.5, which makes sense. We have 0.5, half a credit for each fire station. And when I run this tool, what we end up with are these little travel areas. And you'll see, by contrast, we are actually a lot less covered than we maybe thought we were with just the buffers. And so as I minimize these buffers out, you can see in some of these areas, if we're trying to figure out where should I place a new fire station, I'd probably be looking kind of in this area. We see a lot of buildings, a lot of people maybe in this spot, and maybe not enough coverage. Again, this is just kind of a tool that we would use to estimate and try to figure out where might we want to place a fire station based on their coverages. So totally different analyses that might make sense, populations, all that kind of stuff may go into this. But at a glance, we can kind of see that these fire stations are able to service these areas fairly well, but can always be improved. And so as I kind of pivot back and maybe hand this back over to Sahara, I did just want to emphasize, obviously natural disasters, emergency response, these things happen all the time. And I feel like it's very relevant for us as GIS professionals trying to look into options for how we can better serve those emergency responders. What can we be doing to help them make their lives easier? And I think the GIS world, where we have so much technology and so many tools we can use for both planning, all kinds of different types of management and urban design, right? I think it's really important that we use the tools that we can to help people in times of need.